Hello everyone, welcome to the last minute revision video for Unit 4 exam. So I started making this PDF a really long time back, and that's when I realized that Unit 4 is humongous, the syllabus is huge. So I've tried to cover most of the topics that you might face in your exam, and the ones that I could not cover in this video, don't worry, I have given that in another PDF, and we'll be calling that most important question and answers compilation. So that's a PDF, and you'll get the download link in the description below. That's very comprehensive. All right, and let's look at the topics of Unit 4. So Unit 4 has momentum, circular motion, electric field, magnetic field, and particle physics. Let's look at momentum. So it's a very straightforward question. A is initially in motion and collides with B, and after the collision A and B both move away. So you have to recall a concept from your AS, that is resolving vectors. So you can solve this question in two separate ways. One is resolving vectors, the other one would be scale vector diagram. So let's look at resolving vectors first. So let's say if this angle is given, so this, let's call this final velocity of A, will actually have two components. One would be, let's say this is theta, so this is VA cos theta, and this would be VA sin theta. And let's say if the angle is with the horizontal, and let's call this final velocity of B, this would be this cannot be theta, this should be maybe something, actually let's call this theta 1 and let's call this theta 2. So the horizontal component would be VB cos theta 2, and the vertical component would be VB sin theta 2. Now resolving is done. When we are dealing with momentum, when we say total momentum before collision equals to total momentum after collision, you have to throw in a word when it comes to A2, that is linear momentum. So you cannot consider the momentum in all directions at the same time. You have to consider either horizontal direction or vertical direction. So when you say total momentum before collision equals to total momentum after collision, you have to specify total momentum in the horizontal direction equals to total momentum after collision in the horizontal direction. Similarly, total momentum in the vertical direction equals to total momentum after collision in the vertical direction. So let me show you one example. Let's consider all of these A's and B's have masses MA and let's say MB, right? So this is mass of A and mass of B. So let me just give you one example. If I consider the vertical aspect of it, so vertically, so this was moving horizontally, so there was no vertical motion. So total momentum before collision was actually 0 in the vertical direction, but after the collision this one went vertically upward and this one went vertically downward, considering the vertical aspect of the motion. So MA VA sin theta 1 plus this is downward, so you have to consider this in the equation as well. So MB minus times minus VB sin theta 2. This is how you do calculations with law of conservation of momentum, specifying the vertical and horizontal aspect of the motion. So this was done in the vertical aspect. Now the same thing in the horizontal aspect. Let's see what's going on horizontally. So horizontally, let's say this was traveling with initial velocity u. So total momentum before collision would be MAU, and total momentum after collision is MA times VA cos theta 1 plus the horizontal component of this one, MB VB cos theta 2. There you go. One last suggestion. When you are doing this using vector resolving, always consider horizontal aspect or vertical aspect. Do not mix them up. So this is one way of solving these questions. The other one would be using scale vector diagram that you had already learned in your AS. So what happens with scale vector diagram? So let's say this was the momentum of A. So this was momentum of A before collision. Let's call that BC, before collision, and B is over here and A is over here. So this will be momentum of B after collision, and this would be momentum of A after collision. So of course all of these have to be done to scale to calculate this. So this is the second way of doing this. Of course the angles and everything must be given for you to draw a scale vector diagram. And as always, while drawing scale vector diagram, remember the vectors must be arranged tip to tail, so you can clearly see the tip of B is aligned with the tail of A. Then you have a different context but the same concept. You can apply vector resolving or scale vector diagram, either one works. So momentum and kinetic energy are very closely related. How are they related? The equation that links momentum and kinetic energy is Ek equals p square by twice m. This really comes in handy in a lot of scenarios. Always remember the equation that links kinetic energy and momentum is Ek equals p square by twice m. So from this equation you can see the momentum is doubled, the kinetic energy will be 4 times, quadrupled. Then you have elastic and inelastic collision. While dealing with elastic and inelastic collision, you just have to consider one specific form of energy, and that is kinetic energy. Always remember, in an elastic collision, kinetic energy is conserved, and in an inelastic collision, kinetic energy is not conserved. So before moving on to circular motion, let's look at this. Let's say if this was an elastic collision, so you can clearly see kinetic energy of alpha before collision would be equal to kinetic energy of this alpha particle after collision plus kinetic energy of this proton after collision. You might be wondering, wait a second, so these are in different directions. Do I consider components? No, you don't have to. The reason is you're dealing with energy. Energy is a scalar quantity. You only need to deal with components when it comes to vector quantities. When it comes to scalar quantities, you don't have to consider components. Now let's move on to circular motion. You can see a car is moving along a circular path. Now, a question says a passenger in the car made the following claim. When the car was traveling at high speed around the circular path, I was thrown outwards due to a force acting on me. The outward force acting on me was the centrifugal force. The mythical force we refer to as centrifugal force. As is the claim made by the passenger. No, there is no such thing called centrifugal force. What the passenger felt was actually inertia. So the upper part of the body is not in contact with anything, right? So the upper part of the body keeps on moving in a straight line, but the lower part of the body, especially um, is lower part of the body is in contact with the seat. So the seat provides frictional force which acts like the centripetal force. So the centripetal force acts towards the center of the circle. So the lower part of the body doesn't feel that it is being thrown away, but the upper part of the body keeps on moving in a straight line because there is no force on the upper part of the body. So that's what this person perceives as centrifugal force. So of course the claim is not correct. Then let's deal with circular motion in context. So a lot of people sent me this question and asked me, they're having a very hard time figuring out what's going on with this. So in questions associated with circular motion and angles, my suggestion would be always draw on the diagram, especially the angles. The moment you get to identify the angles, I think the whole thing will be very easy for you. This is the front view of an aeroplane. This is the wingspan, and let's say this is the weight of the aeroplane. All right, this is the weight. Now let's draw a few things here. Always remember, if this is 20 degree, this will also be 20 degree. And if this is 20 degree, this is technically vertically opposite angle. So this will also be 20 degree. So this lift actually has two components. One would be the vertical component, which is, let's call this L cos 20. The other one would be the horizontal component. That would be L sine 20. Now, these two components play two separate roles. So the vertical component, L cos 20, is actually balancing the weight. So L cos 20 equals mg. And the horizontal component, L sine 20. So the plane is turning, of course. That's why it's banking like this. The plane is turning and it's part of this circular motion. So you can see L sine 20, the component of lift in the horizontal direction, acts towards the center of the circle. So L sine 20 provides the necessary centripetal force. So L sine 20 equals mv squared by r. And you can do some basic trigonometry and algebraic things here. You can cancel out the two L's if you divide equation 1 by 2, and you can clearly see the m's get cancelled out anyway, and sine 20 by cos 20 gets you tan 20 equals v square by r goes down rg. So let's say if you had to calculate the radius or the velocity, you can substitute the values into this equation. Again, the most important part was identifying the angles. A lot of people struggle with this question because they couldn't identify these angles. You must have seen these in roller coasters or in viral videos that you can swing a bucket or a glass filled with water in a vertical circle and the water doesn't fall off. So in either case, you have to consider the minimum velocity it requires. But the minimum velocities are different at the top and bottom. In vertical circular motion, the minimum velocity required at the bottom is root over 5gr, and the minimum velocity at the top is just root over gr. The derivation is clearly shown here. You can pause the video and go through this. For minimum velocity at the bottom, I have considered law of conservation of energy here. And for minimum velocity at the top, okay, this part is very important. Minimum velocity, when it's traveling with the minimum velocity, there is no reaction. There is no reaction from the bucket or the glass on the water. So at the top, the only force that provides the necessary centripetal force is actually the weight. So mg is the weight, and weight alone provides the necessary centripetal force. Bear in mind, this is only for minimum velocity. Okay. Derivations are important. This has appeared in several examinations previously. Let's move on to electric field. So electric field can be of two types. One would be uniform electric field, the other one would be radial electric field. So I have taken this diagram from a recent paper. So the two plates here, there is a uniform electric field between the plates and a radial electric field around this sphere. So how do you draw those? When it comes to uniform electric field, the field lines must be straight, parallel to each other, and equally spaced. And field lines start where the plates start. And field lines always flow from positive to the negative. So 0 here means this is the negative plate. And when it comes to radial electric field, if let's say this is a positively charged particle, so lines will be radially outward. Lines will be radially outward. Again, 4 lines is sufficient, but the lines must be straight, equi-spread, and starting from the surface, not the center. So now you have a clear picture of what a uniform electric field and a radial electric field looks like. Then you have a concept of electric potential or equipotential. So do not mix up field lines with equipotential lines. So I have two diagrams here. This is charge 1, and let's say I have charge 2 here. Charge 1 is positive, charge 2 is negative. So in charge 1, the diagram shows the field lines, and guess what? There will be equipotential lines around charge 1 as well, and this is what the equipotential lines would look like in the center. Similarly with charge 2, these are the field lines. Okay, always remember, when it comes to a positive charge, field lines are radially outward, and when it comes to a negative charge, as is the case for charge 2, field lines will be radially inward. And equipotential lines are always perpendicular to field lines. So if you actually try and draw the field lines into this, you'll see at any given point the equipotential lines are perpendicular to the field lines. They make an angle of 90 degrees. So when it comes to the values, always remember, if the charge is positive, the potentials will have positive values. If the charge is negative, the potentials at the surface will have negative values. And the equation for electric potential is V equals KQ by R. So you can see as you move forward, okay, I can give you some reference values. Let's say this is 10, this would be maybe 5, and this would be 2. As you go away from the center, as the distance from the center increases, the electric potential V decreases. I know this equation is very similar to electric field strength equation, which is kq by r square. A lot of people mix this up. Make sure you don't. And if you look very closely, you'll see if the charge is positive, the electric potential will also be positive. And for this one, if the charge is negative, the electric potential will also be negative. This is a very, very, very important concept. Energy conservation and electric potential. So here you have an alpha particle approaching a gold nucleus. Okay, so the alpha particle, since it's moving, has a kinetic energy. We all know the charge on an alpha particle is positive and a nucleus is also positive. So as the alpha particle approaches the nucleus, it's continually being repelled. So the kinetic energy decreases, and at point P it comes to rest. And we know, according to the law of conservation of energy, this kinetic energy cannot just disappear into thin air. This kinetic energy gets transferred into some other form of energy. And guess what? That would be electrostatic potential energy. All right. So we can start working with this. So a lot of times a question asks, what is the minimum distance between the gold nucleus and the alpha particle? Let's say this distance is r. A lot of times a question asks you to calculate this r. So I'll show you my personal favorite method using conservation of energy. So let's recall the concept of electric potential. So one equation is V equals kq by r, and electric potential actually has another equation. So electric potential has two equations. One would be kq by r. The other one is V equals potential energy per unit charge. You might be wondering why I have given two different Qs. So this is the potential for the gold nucleus away from its center. So this equation is the intrinsic equation, right? So I'm using the gold nucleus's values. So that's why the Q will be for the gold nucleus. And the other equation for electric potential is electric potential energy per unit charge. This EP is the electric potential energy or electrostatic potential energy per unit charge. So why do I have a different charge here? Because when an external particle like the alpha particle approaches the gold nucleus, this alpha particle gains this potential energy, electrostatic potential energy. So this is when the charge will be of the alpha particle, because the gold nucleus did not gain this potential energy. The alpha particle gained the potential energy. So the charge over here will be of the alpha particle. And you'll see the two values will be equal as well. So kq by r will be equal to ep by q. So if I make ep the subject, ep will be equal to kq by r. And guess what, guys? Since energy is conserved, this kinetic energy is equal to electrostatic potential energy. So my equation becomes kinetic energy, and the value of the kinetic energy is very often given in the question, will be equal to electrostatic potential energy, which we just found out, which will be K QQ by R. You just make R the subject of the equation. I know it's very complicated, but one of the most common questions. Go through this very carefully, solve some questions regarding this. It's a very commonly occurring question in the question paper. Now capacitors. Capacitors are also part of electric field, and these are actually electrical components, electrical devices. So there was an actual question in the question paper. Question went like this: a student said a capacitor is a device that stores charge. So is this a right statement or wrong? You might be wondering, yes, I do calculate charges on a capacitor. This might be a right statement. Actually not. Capacitor is not a device that stores charge. Capacitor is a device that stores energy. The total charge on a capacitor is always zero, whether it's a charged capacitor or an uncharged capacitor. So the charge that you might have calculated previously, that was charge on each plate, right? So one plate becomes positive, the other one becomes negative, and when you consider the total charge, it's always zero. Now, capacitors, just like any other electrical components, can be connected in series or parallel, and you might have to calculate the total charge, no sorry, total charge, the total capacitance in series and parallel. So I have devised a very straightforward and simple trick to remember this. So what I use is I link it with resistors. So capacitors in series is like resistors in parallel, and capacitors in parallel is like resistors in series. So for series, let's recall the equation for resistors in parallel. So resistance in parallel was 1 by R1 plus 1 by R2, right? So capacitors in series would be 1 by CT equals 1 by C1 plus 1 by C2 plus 1 by C3. And capacitors in parallel would be like resistors in series. So CT will be C1 plus C2 plus C3. In recent papers, they have brought back, actually I would say, the concept of tolerance. And when it comes to capacitors, always link tolerance with capacitance. So here you can see this capacitor has a tolerance of 20%. So if you look very closely, you'll see in the capacitor the value is 2200 microfarad, right? 2200 microfarad. So what will be the maximum capacitance, right? So C will be 20% more, that is 120% of 2200, right? And then to calculate the maximum energy, recall the equation for capacitor energy involving capacitance and voltage. This is the voltage, by the way. It's E equals half CV square. Plug in the values, you'll get your answer. And just to remind you, always link tolerance with capacitance. And why did I take 120%? 20% more, because it says maximum energy, that's why. Now let's move on to graphs associated with capacitors. This is a exponentially decaying curve. So if you look at this value, the initial value, it's around 6.2. This is around 6.2. So a question can ask you to calculate the resistance from this, or the time constant. So always remember, time constant is the time taken for the initial value to drop down to 37%, right? So 37% of 6.2 is 6.2 times 0.37. That gets you 2.3. So this is 2, this is 2.2, so 2.3 should be very close to 2.2. So if I go along this line, so the value is 24 seconds, and this 24 seconds is actually the time constant. And what is the generic equation for time constant? Time constant equals RC. And the definition of time constant is the time taken for the initial value, whether it's voltage, charge or current, to drop down to 37%. And in this case that was 2.3. Then we move on to magnetic fields. So both these questions are from two separate recent years, and this question can be a mathematical question or a theoretical question as well, right? So let's say if you start with this one, we have a metal rod suspended between two poles of a magnet, which is placed on an electronic balance, right? So a current passes through this wire or the metal rod. The reading on the balance would change. So in this context, you have to recall the concept of force on a straight current carrying conductor in a magnetic field. So what is the equation for force on a straight current carrying conductor in a magnetic field? The equation is F equals BIL. The actual equation is F equals BIL sine theta. But if the magnetic field and current are perpendicular to each other, then sine theta becomes sine 90, and sine 90 is 1. So in that case, you can just write BIL. This is actually a very commonly appearing concept. The second concept would be, if I connect these two ends to a power supply, why would the value change in the balance? So when current flows through this wire, a magnetic field is created around it, around the wire. The magnetic field around the wire interacts with the magnetic field of the permanent magnets. And what happens when two magnetic fields interact? A force is exerted. And let's say if the force on the wire is upward, right? So the magnet exerts a force on the wire upward, and we all know every action has an equal and opposite reaction. If the magnet exerts a force on the wire upward, the wire will exert an equal and opposite force on the magnet downward, so this would cause the reading on the balance to increase. And just the opposite also holds true. If the force on the wire is downward, meaning the magnet exerts a force on the wire downward, according to third law, the wire exerts an equal and opposite force on the magnet upward. And in that scenario, the reading on the balance would decrease. So that would be your theoretical approach, and this is your mathematical approach. Next, EMF induced across a straight conductor. So if a straight conductor moves through a magnetic field, and EMF is induced across it, and the equation is EMF equals BLV. Again, these two questions are from two recent years. So if the magnetic field strength is given, or magnetic flux density, B, this is the length in this question, and this is the length, D, in this question. You just plug in the values and you'll get your answer. Always remember, EMF induced across a straight conductor moving through a magnetic field is BLV. I have a general suggestion and advice for your exam. Make sure you have all of the equations memorized. Do not rely on the equation booklet behind your question paper. Then we have magnetic force on a moving charged particles. So let's say in both scenarios you have a positive charge entering a magnetic field. The charge is positive in both scenarios, okay? So in the first scenario, the magnetic field is represented with dots. In the second scenario, the magnetic field is represented with a cross. What do these represent? A dot represents magnetic field out of the page, and a cross represents magnetic field into the page. And a moving charge particle in a magnetic field, the direction of deflection can be found out using Fleming's left-hand rule. So here, always remember, if you have a positively charged particle, the direction of movement of a positively charged particle is the same as direction of current. So the positively charged particle is going to the right, so the current is to the right as well. This is I, current. And dot represents magnetic field out of the page. This is B, B as in magnetic field. So applying Fleming's left-hand rule, you see the force is actually downward. I see a lot of students struggling with Fleming's left-hand rule when it comes to questions like these. Try this out yourself. Pause the video and try it out yourself. The second one is relatively easier. So here, the charged particle moving to the right. So always remember, a positively charged particle direction is the same as direction of current. So if the positively charged particle is going to the right, the current is to the right, and the middle finger represents current. And the index finger pointing into the page, meaning the magnetic field is into the page. So if you apply Fleming's left-hand rule, you'll see the force is actually upward, and that's why this particle deflects upwards. And the equation for force on a moving charged particle in a magnetic field is F equals B Q V. This is definitely useful, but a more useful equation is of momentum of a moving charged particle in a magnetic field. And the momentum of a moving charged particle in a magnetic field is P equals B Q R. I see a lot of students mixing up BQV and BQR. Now that you have the two equations right in front of you, do not mix them up. I repeat, force on a moving charged particle in a magnetic field is BQV, and momentum of a moving charged particle in a magnetic field is BQR. Then you have Faraday's law and Lenz's law. What happens is, if the magnet is moved in front of a coil connected to a bulb, as the magnet moves, as in approaches the coil or moves away from the coil, there is a change in flux linkage when it's moving, of course. And any change in flux linkage with the coil induces an EMF. This part is very straightforward. I'm pretty sure you know this by now. No issues there. But let's address the Lenz's law aspect of it. So this induced EMF, since it's a complete circuit, drives a current. This current creates its own magnetic field. And guess what? According to Lenz's law, any current driven by an induced EMF opposes the change that is causing it. So who is creating this current in this coil? It's the motion of this magnet. So the motion of this magnet will always be opposed. So look at this. When the magnet is approaching the coil, this coil will produce a south pole here so that its motion is opposed. And you can clearly see this by the interaction of the field lines. And when the magnet is trying to move away, This coil produces an opposite pole, and this north is actually attracting this magnet. Magnet is trying to go to the left, but this coil is attracting the magnet, as in it is opposing its motion. That's what Lenz's law does. It always opposes the change that is causing it. This was the simplest way of looking at Lenz's law. There are several important examples, common examples in the PDF booklet. Go through that, and there are some really important explanations over there as well. Then let's look at some applications of Faraday's law. One would be metal detector, the other one would be guitar pickup. So metal detector, what it does is you have two circuits here. One is a transmitter circuit, the other one is a receiver circuit. So the transmitter circuit sends a pulse, electrical pulse. This creates a magnetic field around the transmitter coil, right, momentarily. This field cuts through metal objects nearby. So there is a change in flux linkage which induces the EMF and EMF across the metal object. A current is driven through the metal object. This current creates a magnetic field around the metal object which cuts the receiver coil. There is a change in flux linkage with the receiver coil. EMF is induced, and this drives a current, and this current is fed to this receiver circuit, and it creates a sound. I know, very complicated. Then you have guitar pickups. So we are considering this portion. Let's say this part, when zoomed in, is what you get over here. So you have a coil wrapped around a magnet, and this is the guitar string actually, and this only works with steel strings. So this is a magnet, and this wire, while in the presence of this magnet, becomes magnetized by induction, and when the string is plucked, the wire moves up and down, vibrates. So you just think of the wire as a magnet moving up and down in front of a coil. As the magnet, as in the wire moves, or magnetized wire moves, there is a change in flux linkage with the coil, which induces an EMF, and this EMF drives a current, and this current, when fed to the amplifier, produces the sound. Next we move on to particle physics. Very first part would be probing matter. So in probing matter, this is a question. It says in 1927, J.J. Thomson's son, J.J. Thomson is actually the person credited with the discovery of electrons. So let's see what his son did. Directed beams of electrons at thin films of metal. The photograph shows one of the patterns observed. Explain how this pattern changed scientists' understanding about the nature of electrons. So what pattern do you see? It's a diffraction pattern. Point 1. Diffraction is a wave phenomenon. This means electrons have wave-like properties, or electrons can behave like waves. Then, actually, chronologically, alpha particle scattering experiment was prior to the electron diffraction. So let's see. In the alpha particle scattering experiment, we got to learn about the structure of an atom. Previously, J.J. Thomson actually came up with a wrong model of the atom that was called the plum pudding model. So this plum pudding model was ousted by this alpha particle scattering experiment done by Sir Rutherford and two of his students. They were Geiger Marsden, and I forgot the other one's name. So I have tried to arrange this in pairs. So there are 3 observations and 3 conclusions of this alpha particle scattering experiment. So first observation would be most of the alpha particles pass straight through with little or no deviation. This means most of the space inside an atom is empty. That's the first observation and the first conclusion. Second, few alpha particles were scattered by small angles. So there is a concentration of the charge in the atom. That is the second pair of observation and conclusion. And finally, very few alpha particles were deviated by more than 90 degrees. So this can only happen if the alpha particles were undergoing head-on collisions with the gold atoms nuclei. So most of the mass is concentrated in a small region of the atom. So most of the mass is concentrated in the small region. This region is what we now call the nucleus, and the model that they came up with after this experiment is actually called the nuclear model. So this is not where we stopped. After probing matter, we kept on probing, and for probing matter, probing into smaller matter, we had to accelerate particles to very high energies, and this is why we have particle accelerators. So you only have 2 accelerators in your syllabus. One would be a LINAC, the other one would be a cyclotron. Always remember, LINAC only uses electric field, whereas a cyclotron uses both electric field and magnetic field. And in LINAC, electrons are generally accelerated, but electrons are only accelerated in the gaps, that is between the tubes. Electrons travel with a constant speed inside the tube, and always remember the time spent inside each tube is always constant, because that has to be consistent with the time it takes for the AC supply to switch the polarity. So since the electrons travel with a constant speed, let's recall the equation for constant speed inside the tube, right? So speed equals distance. Distance is basically the length of the tubes by time. So the time is constant always, but after every gap, crossing every gap, since the speed increases, the distance must increase. And guess what? This is why the length of the tubes increases. To keep the time constant, as speed increases, the distance must increase. Distance is the length of the tubes. And when it comes to cyclotrons, the particles are accelerated between the Ds. These are called Ds, by the way. These are Ds. Particles are only accelerated between the Ds. And there is an electric field only between the Ds, but there is a constant magnetic field acting on the particles, perpendicular to the direction of its motion, causing it to move in a circular path. After you accelerate the particles to very high energies, you make them collide. And there are 2 types of collisions in particle physics. One would be stationary target, the other one would be colliding beam. But if you want to create particles with large masses, you have to go with colliding beam. That's because if 2 approaching beams have the same momenta, magnitudes of momenta, the total momentum before collision can be 0. And according to the law of conservation of momentum, total momentum after collision is also 0. And if stationary particles are produced, all of the kinetic energy has been converted to mass. So that's how you get particles with large mass with colliding beams. I have arranged this answer very carefully in the fact sheet. Go through that. This will help you a lot. After you create particles, these are subatomic particles, remember. You cannot see these particles. So how do you study them? You study them using particle detectors. So let's look at a question. In the diagram shows the tracks produced in a bubble chamber. So there are mainly three types of chambers. One is a bubble chamber, one is a spark chamber, one is a cloud chamber. So it starts with this incoming charged particle, okay? And this incoming charged particle decays at x. You can see it produces only one track, but guess what? There was another particle produced here. But why do you not see a track for this particle? Because this particle did not have a charge. Only charged particles produce tracks. Uncharged particles do not produce tracks. So at x, an incoming charged particle interacts with a stationary proton. Okay. Two particles are produced. One is this one, the other one is this one. One is uncharged and therefore does not produce the track. I'm talking about this one. The charged particle has the same charge as the incident particle to conserve charge. We'll be discussing conservation laws shortly. So in any interaction, charge must be conserved. So this doesn't have a charge. So the incoming charged particle and the particle after x, this one, must have the same charge. Now let's talk about the uncharged particle. So the uncharged particle decays at y. What happens at y, everybody? So to conserve charge, if the total charge was 0, the total charge after must also be 0. So you have two particles with opposite charges, one positive, one negative. And since the whole thing is mounted in a magnetic field, two opposite charges will always deflect into opposite directions. So let's look at the points for y. A neutral particle decays into two charged particles. Tracks curve in opposite directions because particles are oppositely charged. Particles have equal and opposite charge to conserve the charge, of course, because the total charge before was 0, the total charge after must also be 0. Now, particles have equal magnitude of momenta since their radius of curvature is the same. I showed this previously. So do you remember the equation for momentum of a charged particle in a magnetic field? It's P equals B Q R. By I, you can clearly see these two tracks have the same radii of curvature, so they must have the same magnitudes of momentum. Now let's move on to the standard model. So standard model actually follows the symmetry. There are 12 fundamental particles. We also call them the building blocks or elementary particles, categorized into groups of quarks and leptons. And these are also organized in generations. They exist in pairs in generations. So there are 6 quarks and 6 leptons. Let's look at the names. Up, down, charm, strange, top, bottom. These are the 6 quarks, and you have 6 leptons: electron, electron, neutrino, muon, muon, neutrino, tau, tau, neutrino. So I made this table so you have a very clear understanding of the generations in which they belong. Up and down belong in the first generation of quarks, charm and strange belong in the second generation of quarks, top and bottom belong in the third generation. Same goes with leptons. Now, when it comes to quarks, they generally exist in groups of either baryons or mesons. So you have to remember the quark structure of baryons and mesons. Baryons consist of 3 quarks or 3 antiquarks, and mesons consist of a quark and an antiquark. Now, in any interaction, there are several conservation laws to be considered. Let's look at them. One is conservation of mass energy, conservation of charge, conservation of momentum, conservation of lepton number, conservation of baryon number, and finally, conservation of strangeness. Take a look at this example, right? So you have a neutron decaying into a proton and an electron. Forget this, guys, for the time being, of course. So if you had just this bit, you say that the neutron has 0 charge proton has +1 and an electron has -1. You might be wondering, conservation of charge fulfilled, no issues there. But that's the thing, you cannot just conserve the charge, you have to conserve the lepton number over here as well. For example, it's a neutron which is a baryon, which does not have a neutron number, which doesn't have a lepton number. So the lepton number is 0. I'm not talking about charge anymore, I'm talking about lepton number. Let me write down here Ln, okay, lepton number. So the neutron has 0 lepton number. It's a baryon, it does not contain any leptons. Now proton is also a baryon, doesn't have any leptons, so this is also 0. But the electron is a lepton, so the lepton number will be +1. Guess what? This is why you need the anti-electron neutrino. The electron neutrino has a lepton number of +1 and an anti-electron neutrino has an lepton number of -1. So if you had just this, even though charge would have been conserved, but the lepton number would not be conserved. That's why you have this extra bit of plus anti-electron neutrino to conserve my lepton number. Good luck with your exam, everybody. Thanks for watching.